So in the space right beside here, and also I'd like you to highlight polynomial functions. The coefficient of the highest power is called the leading coefficient. And in the space right beside this, we're going to do a little summary. First of all, we're going to do a little summary for odd functions. Those are where the highest exponent or highest degree is odd. So there x to the 1 graphs, x cubed, x squared, x to not cubed, squared, x cubed, x to the 5, x to the 7, any odd number is the highest exponent. And we're going to talk about the end behavior acting like a line. If the leading coefficient is positive, positive slopes for lines, your end behavior starts down there, ends up there. If your leading coefficient is negative, well, a line with a negative slope goes down, it would start in the top left and go down to the bottom right. Now, if you have an x to the 7 graph, it might have a whole bunch of hills and valleys in between, and then end in the same place. So right now, we're just finding out how do we tell where graphs end. And same thing, we can add a note about even functions. That's where the highest exponent is even. And your most basic even function that you've already done is a parabola. So we can say that the end behavior acts like parabolas. If you have a positive leading coefficient, any even-powered one will end opening up. And if you have a negative leading coefficient, that's when parabolas open down, then your end behavior will open down. And this is true for any even or odd function. So if we go through the listing that they have, so this starts on page 39, they start off with a line. A line is an odd function, and it's going to act like a line. Surprisingly, that lines act like lines. If you have a leading coefficient that's positive, your end behavior, just like a positive line, has a positive slope, ends there. And if it's a negative leading coefficient, it goes down like that. Next, quadratic, these are our parabolas. That's our first even degree one. If in front of the x squared you have a positive leading coefficient, it opens up. And if you have a negative leading coefficient, it opens down. Now these are ones you've done already. But we're going to see that this pattern stays the same as you keep on going. So if we went to our x cubed graphs, positive, I would think of a line, I would think of my end behavior, and sure enough, does that not match up? Starts in the bottom left, ends in the top right. I would think of a line if it was a negative leading coefficient. My end behavior should start up here and end bottom right. Yes, it does. So we can simplify everything just to lines and parabolas for its end behavior. Power of 4, these are called quartics. If it's positive, I think of my parabola. Positive parabola would open up in both directions, and sure enough, this one does. And a negative leading coefficient means that it should open down, and this one does. What happens in the middle, we're not quite sure how to do that yet. Like the one turned out to be a W, the second one just had this like weird bend in it. So we're unsure how we can show those things right now. But if we're just worried about the end behavior, and then they have x to the 5. So again, if it's positive, I think of a line. My end behavior should start down here. It does end up here. And if it's negative, it's odd. It acts like a line. It should start up here and down here, and it does. And what's happening in the middle, well, some of it we're going to be able to do with grade 12 pre-calculus, and some of it you have to wait till next year when you do curve sketching in calculus. So to really graph this well, some of us will need some calculus to do that. But we're going to try the best that we can with what we know so far. Some more things to highlight. Okay. Odd degree polynomial functions. Here, instead of writing this, like you can memorize this if you want to, but I think with odd degree it is so much easier to draw the line and think of the end behavior. I think this picture definition is way easier to memorize and know, rather than as x goes to negative infinity, the graph falls to the left. And as x goes to positive infinity, the graph rises to the right. It's a true statement, but I think the picture really explains it quite quickly and quite easily. Same thing with even. I would just go to my parabolas. And instead of remembering this, I would draw a little picture of a parabola and say, there's my end behavior. Has to be going up, whether I go to positive infinity or negative infinity. And same thing with this one. If it's negative, there's my end behavior. And one last thing to highlight before we get to example 1. Sometimes we say graphs have local minimums or local maximums. This point right here is a local maximum, and technically in this graph, it's the absolute maximum. It's the highest that graph ever gets. But we still call them local maximums, and the idea is if you drew a circle around them, it's the biggest in that circle. If you just take your neighbors that are close to you, someone's a maximum. There's somebody who is the tallest in this class. They are not the tallest. Well, I don't know, but I'm pretty sure that the tallest person in the school is not in this class. They're most definitely not the tallest person in Winnipeg. But there is a local maximum in this class. Someone who is the tallest. Right? There's also a local minimum. Someone who has the smallest big toe in this class. There's somebody, if we measured everybody's big toe, somebody would have the smallest big toe, and they would be the local minimum in this class. But most likely there's a baby in Winnipeg with a smaller big toe than you. So you're not going to be the local minimum for Winnipeg. And then probably somewhere in the world, there was just born a very, very premature baby with the tiniest big toe ever. And they are currently the world leader for smallest big toe. But we talk about local minimums and local maximums just in that small area. It's the biggest or the smallest. Okay, so I think we're ready to go to example 1. And we want to sketch these graphs the best that we can with the skills that we have right now. We're going to learn better skills to do this. But right now, if I was graphing A, draw my graph, the first thing I would notice is that it's an x cubed graph. And because it's an odd one, I would know that my end behavior looks like this. That much I know. So I know that it's going to start down here. I'll draw it in blue. I know there's going to be an arrowhead down here. It's going to end up somewhere over here. I just have to figure out what the heck is happening in the middle as best that I can. And at this point, the best that we can do, and a very good strategy, but usually the longest as far as how long it takes, is draw a table of values. Does it make sense that the more points you plot, the more accurate you're going to be? Right? So if I just plugged in 0, I like that point. When x is 0, y is 0. I feel really good. Does that tell me what the whole graph looks like? No, but I know that it's going to start down here, go through that point, and then go up to there. I could plug in other points. Mental math-wise, I think 1 would be easy mental math. 1 cubed minus 3 would give me -2, so now I know that, okay, 1, -2. If I plug in 2, I would get 8 minus 12, -4. If I plug in 3, I get 27. Minus 27 is 0 again. That's kind of nice. If I go to the negatives, -1, that'll give me -1 minus 3, -4. And at some point, where's -1, -4? At some point you decide, okay, I think I got an idea that it's going to start down here. Well, it looks like, maybe I draw this over a little bit. It's going to go down like this. I don't know. Something like this as an idea. I'm not for sure. Okay? I might be wrong. I don't know that this is the smallest it ever gets. Is 2, -4 the local minimum? I don't know. It's just a point that I got. I've kind of made it look that way, but I'm not sure. If I plugged in 2.1, maybe it would go lower. Or maybe it got lower before 2. Maybe 1.9 is lower. We can take out our graphing calculator and actually take a look at this. So I have x cubed minus, what was it? Minus 3x squared. Okay. And if I actually use my calculator to find the minimum, between these two. Is it at 2? It is. 1.999 happened to be perfectly at 2. Got lucky that way. Sometimes you'll find it isn't exactly at that point. So right now, all we have is a bunch of points, and for sure I know this and this. So we're not going to do part B right now, but in part B, you see it's a -x⁴. So you know the end behavior would act like this. What's annoying about the table of values? It's going to just be a lot of mental math, right? You probably plug in 0, that would be easy. That'll find your y-intercept. Probably plug in 1 and -1 so you don't have too hard of mental math. But once you get to 2s and 3s, the numbers get quite big quite quickly and become a little bit more challenging. Of course, then you can also go either to a graphing calculator or you can use Desmos online. I don't know if you've ever used the Desmos program for graphing. You can download the app as well. See if I've got it up here. So, Desmos is as easy as this. So we're going to look at this one. I'm going to go y equals, and it was a -x⁴ minus 6x cubed minus 9x squared plus 3. And Desmos is nice because you can zoom in and out, you can move it around. Looks like I'm really zoomed out right now. So I can scroll in. And what also is really nice about Desmos is if you click on the graph, it automatically, I don't know if you see it there, but it's got all of these, it's like these look like important points, intercepts, and maximums, and you can just click on them and it tells you where they are. Super nice, super fast. And so that is really helpful because we didn't have to, I mean, you could have done a table of values. We figured 0, 3 out. You probably would have figured out -3, 3 if you did enough points. But I don't think you'd ever find any of these x-intercepts with guessing and checking on a table of values. All right, so questions to circle for number 1 are 5, 6, and 8.